In this unit, we're going to review the big ideas from our unit covering sequences and series. So we began this unit by discussing sequences. Remember, sequences are lists, whereas series are sums. So we're going to figure out whether these sequences are convergent or divergent, and we are going to do that by finding the limits. So find the limit as n goes to infinity of n squared over e to the n. Well, we're going to want to use L'Hopital's rule, so let's change our n to an x. And this is an infinity over infinity limit. So this equals the limit as x goes to infinity of 2x over e to the x, which if we do it again, is the limit as x goes to infinity of 2 over e to the x, which is equal to 0. And thus the sequence a sub n converges to 0. Here, let's find the limit as n goes to infinity of this list. E to the, that is 3n squared over n squared plus 1. So that's the same thing as e to the limit as n goes to infinity, 3n squared over n squared plus 1. And so the stuff inside the exponent goes to 3. So this goes to e to the third. So the sequence a sub n converges to e to the third. Be careful, don't confuse this with series. The sum of the a sub n's would diverge, but the sequence of a n's converges to e to the third. You've got to keep those two things straight. A sequence would diverge, or at least fail to converge. So it can fail to converge in at least two ways. Way one would be that the limit as n goes to infinity of the terms is either infinite, or another possibility could be that as n goes to infinity, those terms are going to oscillate. For example, if your a sub n was something like sine of, I don't know, pi over 2n, those terms would flip-flop between -1 and 1, and also 0, and they're never going to go a specific place. So that's how sequences will fail to converge / diverge. So after sequences, we delved into series, and the first things we learned were how to find the sums, actually find out what these things add up to for very specific series. The series that you know how to find the sums are geometric, telescoping, and things that are common Maclaruin series. So if you're going to use a geometric series, you want to find out what that sums to, your series must begin at 0. So notice how this one begins at 1. So let's re-index it so it starts at 0. So you re-index and it becomes 2, -3 to the n plus 1 over 4 to the n plus 1 plus 1. So peeling this off into the a, the constant, and the r, we have 2 times -3 over 16, because that was 4 squared, times -3/4 to the n. So notice that the a is -6 over 16, which is -3/8, and the r is -3/4. And as the absolute value of -3/4 is less than 1, this thing converges to a over 1 minus r, and that is -3/8 over 1 plus 3/4, or -3/8 times, that would be 4/7, because the denominator adds up to 7/4. And this simplifies to -3/14. So be able to recognize when you have a geometric series and figure out what it actually converges to. Now the second one obviously isn't geometric. It's not just a number raised to a power of n. So these terms appear to be awfully close to each other. Like one of them, the denominator is one bigger than the other. So a good candidate is telescoping. And how you find this sum is you list the nth partial sum. So what do you get when you add up the first n things? Well, if we plug in 1, we have e minus e to the half. That's the first term. Plug in 2, we get e to the half minus e to the third. And look, this and this cancel. Just do one more, plug in 3. We get e to the third minus e to the fourth. And notice how this guy and that guy cancel. So you keep adding them up all the way until you add up your nth thing, which is e to the 1 over n minus e to the 1 over 1 plus n. One prior to that will be e to the 1 over n minus 1 minus e to the 1 over n. And notice how this guy and this guy will cancel. So the only terms left when we've listed out this nth partial sum are e, and the last term, e to the 1 over 1 plus n. And so now this is the sum of the first n things. If you want to add up the first 100, 1,000, million, trillion, billion. If you want to add up an infinite number of things, the actual sum will equal the limit as the number of things you're adding goes to infinity. And if you take a limit as n goes to infinity of our formula for adding up the first n things, limit as n goes to infinity of e is just e, and this exponent in the e is going to go to 0, so e minus e to the 0, or e minus 1. And for telescoping series, there's absolutely no way around it. You have to list the nth partial sum, and you will have to do it correctly. All right, now we have a whole bunch of things where we're going to test them for convergence or divergence. You've got to pick out which test you're going to use. So this one, that square root sign, should actually go over everybody. All right, so this looks kind of like it could be a p-series if I had fewer terms. If you see anything p-series-like, and you want to do a comparison test, and if you don't want to make an inequality statement, your best friend is the limit comparison test. So we're going to let a sub n be the terms in your series. And b sub n be the terms of a simpler series that you know something about. And the way that I think is best to find that is to take the highest order terms in the numerator and denominator. N squared over root n to the 10th, which is n squared over n to the 5th, or 1 over n cubed. And then this limit comparison test says to find the limit as n goes to infinity of the ratio of these terms. And if this limit is a positive finite number, then you know that the series sum of a n's and sum of b n's do the same thing. Okay. So a n over b n is the same as taking a sub n multiplied by the reciprocal of b sub n. That will be n to the 5th minus 3n to the 4th over the square root of n to the 10th minus 4n squared plus 1. Now multiplying by 1 over n to the 5th, 1 over n to the 5th, when that 1 over n to the 5th goes inside the square root sign, it must get squared, and it becomes a 1 over n to the 10th. So that gives us root 1 minus 4 over n to the 8th plus 1 over n to the 10th. And that limit will be 1. And this number just needs to be a positive finite number. It's bigger than 0. Thus, by the limit comparison test, I'm going to make a mistake here. AN converges as Bn is a known convergent series. So the mistake that I made was this, is if you don't put those sum signs, they were talking about a sequence, not a series. So this is how you do it right. As the sum, so by the limit comparison test, you know the sum of the A sub n's will converge as the sum of the B sub n's is a known convergent series. So you have to have the sum signs there if you're talking about a series. If you're talking about a sequence, you do not have the sum signs. And probably best to say n equals, it was 1 to infinity. So probably best to give those some bounds, because it would actually affect what it adds up to. Not that it added up, but 1 to infinity. N equals 1 to infinity. Now, another test you will have to use at some point in time probably is the integral test. So you know to use this test when you see a function that you can probably find the antiderivative of. And there are 3 requirements for this test. Is your function f of x, which in this case is going to be x e to the negative x squared. It must be continuous. And this one is everywhere. It must be positive, and that is true for x is bigger than 0 in this case. And it must be decreasing. And in the case of this particular example, you can't say it is obviously decreasing because you have, it really is a ratio. It's x over e to the x squared, but you have variables in the numerator and denominator, so you're actually going to have to sometimes prove this using a derivative, and that is the how you prove it. I'm not withholding some special trick. You have to prove it using the derivative. So let's find the derivative using the product rule. The derivative is 1 e to the negative x squared plus x e to the negative x squared times negative 2x, or e to the negative x squared times 1 minus 2x squared. This will be less than 0 if this 1 minus 2x squared is less than 0. That implies that 1 is less than 2x squared, a half is less than x squared, and we only care about positive x's, so for us this is true if x is bigger than 1 over root 2. So you know f is decreasing on 1 over root 2 to infinity. And the point for this stuff is this must decrease eventually. It doesn't have to decrease the whole time, just must be some point, and from that point on, the function is decreasing. And once you know that, you can apply the integral test. And to do this, you find the improper integral. You integrate from 1 to infinity x e to the negative x squared. So that's the limit as b goes to infinity, integral from 1 to b x e to the negative x squared dx. To evaluate this integral, we're going to use a substitution. We're going to let u equal negative x squared. Du is negative 2x dx. If x equals 1, u is actually negative 1. And if x equals b, u is negative b squared. Notice that you square, then make it negative. So negative 1, negative b squared, negative 1/2 e to the u du. All right, so technically negative b squared is a larger number than negative number than negative 1. So let's flip this around. Make this positive 1/2 the integral from negative b squared to negative 1. You don't have to do that if you don't want to, but I think it's helpful. So we have 1/2 e to the u evaluated from -1 to negative b squared, or so we have 1/2 times e to the -1 minus e to the negative b squared, which is the same thing as, almost done, 1/2 times 1 over e minus 1 over e to the b squared. Notice how as b goes to infinity, this second term will go to 0, so this will converge to 1 over 2e. And so your conclusion is, as the integral converges, so does the series by the integral test. Just a note, it does not converge to 1 over 2e, and by it I mean the series. The integral converges to that value, but the series converges to some other value. It might be kind of close to this, but you don't know specifically what it actually is. So this series looks like a good candidate for the alternating series test. And the way that you can tell that is you have something that is obviously flip-flopping. You see a -1 to the n, it might be the alternating series test. No, the ratio test might also work here, but let's use the alternating series test just to show you how that would work. So for the alternating series test, we're going to let the b sub n's be n over 2 to the n, and we're going to find the limit as n goes to infinity of those b sub n's. This limit must equal 0. And we use L'Hopital's rule. And that will be 1 over ln of 2 to the n, and that limit is 0. So first condition is met. Now the second condition, we must have that b sub n plus 1 is less than bn. And really, you'd have to prove this by doing some kind of fancy cross multiplication. So unless you're ready to do that, I think that it is better to use the function f of x equals x over 2 to the x and find f prime of x. That's the whole purpose of a derivative. It tells you where a function is increasing and decreasing. So f prime of x is low d high minus high d low over low squared. And notice that now the 2 to the x's will cancel. 2 to the x squared, and those 2 to the x's will cancel. We have 1 minus x ln of 2 over 2 to the x. This will be less than 0, as in negative, if 1 minus x ln of 2 is less than 0, which means 1 is less than x ln 2, or 1 over ln 2 is less than x. And so thus f of x is decreasing if x is greater than 1 over natural log 2. So the b sub n's are decreasing, and this series converges by the AST. I was so busy looking for an example of the AST that I think I failed to realize that the ratio test would actually also work here, but you can count on there being an alternating series test problem somewhere on your final, so watch for it. If you see something super funky, the first thing you should be checking is maybe this is the test for divergence. And so the test for divergence says if the limit of the terms is non-zero, then the series will diverge because eventually you're adding up things that are very close to that number for an infinite number of times, which will give you infinity. And notice as n goes to infinity, it can migrate inside that cosine, and that stuff inside the cosine goes to 0. And cosine of 0, well, that's 1, and that's not equal to 0. So thus, this series diverges by the test for divergence, or the nth term test. Another pretty easy test to spot is the root test. So let's find the limit as n goes to infinity of the nth root of the absolute value of an. One minus 3n over 3 plus 4n to the 3n. So the nth root will cancel out that nth, leaving us with a limit as n goes to infinity of 1 minus 3n over 3 plus 4n all to the third. And so what we'll have here is the limit as n goes to infinity. It doesn't really matter how we do this. So we can say move the third power outside those absolute value bars. Absolute value bars 1 minus 3n over 3 plus 4n, and then cubed. And as n goes to infinity, the stuff inside those absolute value bars goes to negative 3/4, which then absolute values to 3/4, which then gets cubed, and it is 27 over 64. And you prove this, the result of this test depended upon comparison to a geometric series. So a geometrical series will converge if the r is less than 1. The same thing is true here. This is less than 1. So thus the series converges by the root test. And actually it converges absolutely, which is stronger than just regular convergence. So speaking of absolute convergence, if you prove absolute convergence, this implies convergence always. So for this series, the AST fails because this series does not alternate. As in, it doesn't consistently flip-flop positive, negative, positive, negative. It's sometimes positive, sometimes negative. So we're going to use the fact that absolute convergence implies convergence. So the first thing is we note that the absolute value of sine of 2n over 2 plus n squared, that's less than or equal to 1 over 2 plus n squared, which is less than 1 over n squared. As the sum from n equals 1 to infinity of 1 over n squared converges, the sum from n equals 1 to infinity of the absolute value sine of 2n over 2 plus n squared converges by direct comparison. And this is the definition of what it means to be absolutely convergent. So thus our series from n equals 1 to infinity sine of 2n over 2 plus n squared is absolutely convergent and therefore convergent. Now determine whether these series are conditionally convergent or absolutely convergent or just plain old divergent. Give a short explanation. So this officially is the sum from n equals 1 to infinity negative 1 to the n over root n. This thing converges by the AST. It would be very easy to show. But the sum from n equals 1 to infinity of its absolute values, that's equal to a sum from n equals 1 to infinity of 1 over root n, that diverges. P is bigger than 1. So because the series itself converges, but the sum of its absolute values do not, this is an example of a conditionally convergent series. This next example is the same thing as the sum from n equals 1 to infinity, negative 1 to the n over n cubed. This also converges by the AST, and the sum of its absolute values, well, that's the sum from n equals 1 to infinity 1 over n cubed. That converges since the p is equal to, it's a p series with p equal to 3. This is an example of absolute convergence. Find the sum of the following series. If the series diverges, explain why. So this is the third option for things you know how to find the sum of. These are examples of a common Maclaruin series for basic functions. So if you remember, the series for e to the x is the sum from n equals 0 to infinity x to the n over n factorial. This is awfully close. We just have that negative 1 to the n. The series for e to the x does not alternate. So what we can think about this as, we can think about it as a sum from n equals 0 to infinity, negative 2 to the n over n factorial. And notice how negative 2 is the thing that's been input for that x. So this is equal to e to the negative second, or equivalently, 1 over e squared. So that does require recognizing that you have a Maclaruin series for a common function. Here's another one. So you see the negative 1 to the n and the 2n factorial, and you should think cosine. Cosine's Maclaruin series is the sum from n equals 0 to infinity, negative 1 to the n x to the 2n over 2n factorial. And notice how there's a pi to the 2n and a 2 to the 2n. Well, that's really the same thing as the sum from n equals 0 to infinity, negative 1 to the n, pi over 2 all to the 2n over 2n, the quantity factorial. Notice how pi over 2 was input into cosine. So this is cosine of pi halves. So this series actually sums up to 1. And next, let's find the radius of convergence and the interval of convergence for the following series. So for this, we're going to use the ratio or the root tests. So when you see a factorial, good bet that you're probably going to want to use the ratio test. So find the limit as n goes to infinity of the ratio of an plus 1 over an. Okay, so negative 1 to the n plus 1, x to the 2, parenthesis, n plus 1 over 2 n plus 1 factorial. Dividing by an is the same as multiplying by its reciprocal. And now let's simplify a bit. I'm not going to get rid of the absolute value bars, but I am going to get rid of the negative ones to the n's because they don't really matter. So I have x to the 2n plus 2, 2n factorial over 2n plus 2 factorial times x to the 2n. Now I think it's pretty obvious that when you have x to the 2n plus 2 over x to the 2n, you're going to have x squared. And those absolute value bars aren't necessary because x squared will always be positive. in the numerator we also have this 2n factorial, and the question is how much of the denominator cancels with that? Well, 2n plus 2 factorial, the largest value is 2n plus 2, 1 less is 2n plus 1, and then next you do 2n, and everything lower. So notice how you have two terms here. When I assigned this question, I was actually kind of checking, could you catch that that was the case? So now no matter what x is, as n goes to infinity, you have a number times 0. This will give us 0, which is less than 1 always, no matter what x is. So since x can be anything, this means your radius of convergence is infinite, and the interval of convergence is minus infinity to infinity. And when we did Maclaruin series, I told you that the radius of convergence for this series was infinite, because this is the series for cosine of x. This thing that we just did is the proof of why that is true. This next example, you should apply the root test, and I'm going to warn you that if you try to do the ratio test, I have thus far not seen any student do that correctly because the limit you get is pretty tricky. So if stuff is only raised to the n and there are no factorials, do the root test. So find the limit as n goes to infinity of the nth root of the absolute value of the an's. So x minus 3 to the n to the n. Notice how those n's cancel out beautifully. So you have x minus 3 absolute value times n. Now, this thing, n is going to infinity. Number times infinity, that makes infinity. Unless x is equal to 3. If x is equal to 3, you're summing up a bunch of zeros. So this converges only if x equals 3. That means the radius of convergence is 0, as in that's a 0-widthed interval. And the interval of convergence is just the single value 3 for which this series converges. So the last example of radius interval of convergence has to do with things where we're not going to get infinity or 0. We get an actual finite number. Well, 0 is a finite number, I guess. Something finite and positive. So here we're going to apply the ratio test. This singular n on the bottom is what screws the root test up. So ratio test. Limit n goes to infinity, an plus 1 over an. So negative 1 to the n plus 1, x minus 1 to the n plus 1 over n plus 1, 10 to the n plus 1, multiplied by n, 10 to the n, over negative 1 to the n, x minus 1 to the n. Okay, so the negative 1 to the n's don't matter, and let's cancel some stuff. So we have the x minus 1 to the n plus 1 over x minus 1 to the n. That's going to give us an x minus 1. Next, the n and the n plus 1 don't go away, but the 10's do cancel, so we just have a singular 10 in the bottom. So now that x minus 1 over 10 is constant, and as n goes to infinity, this thing goes to 1. So this limit approaches the absolute value of x minus 1 over 10. And the ratio test tells us that this will converge if the absolute value of x minus 1 over 10 is less than 1, which implies that the absolute value of x minus 1 is less than 10. So your radius of convergence is 10. So you converge for numbers that are 10 greater than 1 and numbers that are 10 less than 1. Now the only tricky thing we have to do is find and test the endpoints. Okay, so since the absolute value of x minus 1 is less than 10, we know that x minus 1 itself has to be between negative 10 and 10, or x is between negative 9 and 11. Notice how the width of that interval is 20, which is exactly double the radius of convergence. And that has to do with the fact that you're centered at 1, and that R says you converge for numbers that are 10 up or 10 down from that number. And now that we know the endpoints, we have to test them explicitly in the series. So test x equals negative 9. When you input negative 9 into the series, you get the sum from n equals 1 to infinity, negative 1 to the n, negative 10 to the n over n 10 to the n, which, combining those two things that are to the n in the numerator, it'll make 10 to the n over n 10 to the n, which is 1 over n. And that thing diverges. You can say it's a p-series, you can say it's a harmonic series, either way. And x equals 11, excuse me, not 10, 11. At x equals 11, we get the sum from n equals 1 to infinity, negative 1 to the n, 10 to the n over n times 10 to the n. And that's the sum from n equals 1 to infinity, negative 1 to the n over n. That would converge by the alternating series test. It's kind of the typical example of a conditionally convergent series. So your interval of convergence does not include negative 9, but does include 11. So like that. Or you could say negative 9 less than x less than or equal to 11. That's the same thing. And next we found power series for various functions, and we have many techniques to do this, one of which involved using a geometric series, another of which involved using derivatives or integrals and a geometric series, and then finally we used Taylor or Maclaruin series to find power series representations of functions. Now the one thing about a power series representation is it has to be something of the form some constants times x minus a number to the n. And the kicker is that actually x must be in the numerator, not the denominator. So for this question, here is how you must do this. You have to rewrite this as x over 9 plus x squared, and you have to write this then as x over 9 over 1 plus x squared over 9. And then you can use a geometric series with a equals x over 9 and r equals negative x squared over 9. This will sum up to n equals 0 to infinity x over 9 negative x squared over 9 to the n. And simplifying that down, so first we'll have a negative 1 to the n. The power on x will be 2n plus 1, and 9 is going to be raised to the n plus 1. And the radius of convergence, we have to have the absolute value of negative x squared over 9 less than 1, which means x squared is less than 9, which means that x is between negative 3 and 3, so radius of convergence is 3. Here is what is wrong. So if you do this, if you divide, instead of dividing, flipping it and dividing by 9, if you divide by x squared, so x over x squared over 1 plus 9 over x squared, and you say that's the sum from n equals 0 to infinity 1 over x times negative 9 over x squared. This is not a power series. It's technical. You've made sort of no mistakes in your algebra and stuff, but for a power series to be a power series, it has to be x to a whole number power, and this is going to be x to negative powers, and so that just is not the definition of what a power series is. Now, another technique we had was to use a derivative or an integral. So notice here that f prime of x is equal to 1 over 2 plus x. So then natural log of 2 plus x, well, that's going to be found by integrating 1 over 2 plus x. And that's useful because this thing that I have inside my integral sign is something that I can actually find a power series for. So that will be 1/2 over 1 plus x over 2. And use a geometric series with a equals 1/2 and r is negative x over 2. So 1/2 times negative x over 2 to the n dx. There's a reason I've been avoiding integrating these things until I've simplified, and it's because it's a lot simpler. So simplify first. This is negative 1 to the n over 2 to the n plus 1 times x to the n. Now at this stage you integrate, and the thing that gets integrated is this x. Everything else is a constant. So the antiderivative of x to the n is x to the n plus 1 over n plus 1 plus some constant c. So there you go. Now figure out what c is. We can plug in a clever value. If we plug in x equals 0, we get on the left side we have ln of 2. On the right side we just have c because everything in that summation is 0. So the constant is equal to ln of 2. So this is the sum from n equals 0 to infinity, negative 1 to the n, x to the n plus 1, 2 to the n plus 1 times n plus 1, plus natural log of 2. And you should also be familiar with how to find Taylor series for functions. So the formula for a general Taylor series is that you take f of a plus the derivative at a times x minus a, technically over 1 factorial but 1 factorial is 1, plus the second derivative at a over 2 factorial x minus a squared, etc. You can think about that as a sum from n equals 0 to infinity, the nth derivative evaluated at a, x minus a to the n over n factorial. I find it easiest to find the first few derivatives, look for a pattern, list it out, and then write it as a sum. So our function f of x is e to the 5x. F prime of x, 5e to the 5x. Second derivative of x, 5 squared e to the 5x. You kind of get the idea. The nth derivative of x will be 5 to the n e to the 5x. Now when you input 2, f of 2 is going to be e to the 10th. F prime of 2 is 5e to the 10th. The second derivative of 2 is 5 squared e to the 10th. Notice every term will have e to the 10th, but that remains constant. The nth derivative at 2 is 5 to the n e to the 10th. So this Taylor series will equal e to the 10th plus 5 e to the 10th times x minus 2. Should have said a equals 2 plus 5 squared e to the 10th over 2 factorial x minus 2 squared, etc. Or a sum from n equals 0 to infinity. So the 5 has a power of n, the x minus 2 has a power of n. We're over n factorial, and e to the 10th is just hanging out there as a constant. So there is your Taylor series centered at a equals 2. If you were asked to find a Maclaruin series, the only difference there is that the a is equal to 0. And that, in a nutshell, is most of the ideas from the sequences in series unit.